These fires do not have to persist, and you don't have to have those dry conditions.
We're here in Santa Barbara County, home to one of the longest running cloud seeding operations in the country. We've got some ground-based cloud seeding equipment right here, and we're gonna get to hear all about how it works and see it in action. Let's check it out. Cloud seeding is the most common type of weather modification, and it has many different techniques and applications. Today, it's mostly used to increase rain and snowfall, reduce the size of hail, and reduce fog at airports.
Traditionally, cloud seeding has been done from the air. So airplanes have had racks on them where these same flares are positioned on the airplane, and the airplane flies into the storm. So in order to reduce the cost to the client and reduce our carbon footprint, we've been able to station these on the ground. Now we can do this in places where weather permits.
Behind a barbed wire fence designed to keep away curious cattle, the cloud seeding gear awaits the right kind of weather.
So these are referred to as AHOGs. That stands for Automated High Output Ground Seeding Systems. We've got three primary components of our equipment here. The first is the control module that you see behind me. Then we have our actual cloud seeding flares. The cameras for security. It also helps us observe weather conditions in real time and make sure that all of the equipment is operating correctly during a storm. Inside these canisters are the flares with the seeding agents. The canisters are used as spark arresters, so they prevent sparks from reaching the ground. So if we pull off the spark arrestor, you can see the flare inside. The ignition of the flares are controlled from the control module that's behind us. So the white triangle there is a cell service modem, and then the solar panel keeps us powered. Inside we have a battery and then a control board. So the control board interacts with the software. We're linked or synced with the software in Utah currently, and that allows us to fire or ignite any of the flares from that remote location.
Because of the lack of clouds and proper wind conditions, today is not a good day for cloud seeding at all. But Garrett and his team are going to light a flare for us anyway, so we can show you how it works. There's just one small problem. The battery in the control module died shortly before we arrived, but it's nothing a little jump start can't fix. After a little juice from Garrett's truck, it's time to set off the flare.
The primary seeding agent in this is silver iodide. Silver iodide is a simple compound. It's polar in nature like water, so there's chemical properties that help attract water molecules to silver iodide. It's also structured molecularly similar to ice. So it helps generate or helps spawn the generation of ice buildup, and then that becomes a hailstone or a snowflake that falls here primarily as rain. So one flare like this has billions and billions of potential sites for that water to congregate around. We'll launch them in sequences. We watch the radar to see when bands of the highest concentration of liquid water are passing above us in the clouds, and we try to target those high concentration pockets in the storm systems. We'll launch between 3 and 20 flares for a typical storm. Once the flare is lit, it takes a little bit of time to carry up into the clouds, and once it's up at the proper elevation, it'll take about 20 minutes to instigate the rain or the snow process. So overall, you're probably looking at about 40 to 45 minutes before you're seeing the maximum result.
This is the shuttle's fuel tank. It may only be 130 miles to space, but to cover that distance, the engines will use 500,000 gallons of fuel, and that works out at 2 feet to the gallon. Despite the cost, however, NASA does need to test these engines once in a while.